Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. We're going to start a sequence of 3 lectures now where we investigate Schrödinger's equation in one dimension. I'd like just to remind you what it is, right? We're going to solve that for 3 very classic situations. It's important that you understand the solutions and know how the solutions to these 3 classic examples are obtained. These next 3 lectures, you really have to work through the lecture notes. You can't just sit down and read through them and assume that you've understood the material. In fact, you probably have to take a piece of paper out and a pencil and work through some of the equations yourself if you really want to understand what's going on. So, having said that, the first problem we're going to attack is the one-dimensional infinite square well. This is a classic problem, and basically the premise is you have to specify this potential energy function u of x, and you have to put this into Schrödinger's equation. And the u of x that we're going to use for this infinite square well is going to be u of x, which is equal to 0 between minus L by 2 and L by 2. And then it goes to infinity at these boundaries, right? So basically you're basically creating a square well, and the boundaries of that square well are infinitely high. And then what you're going to do is you're going to drop a particle in. For the example that we're going to work through, we're going to pretend that particle is an electron, and so we're going to be using the mass of the electron to calculate the allowed energies that this electron can have in this infinite square well. But in principle, the mass could be the mass of any particle that you confine to a region of space. So, having said that, Schrödinger's equation, which explicitly has u of x in it, can now be rewritten because we've defined u of x to be equal to 0 between minus L by 2 and L by 2. And so this is Schrödinger's equation in this confined region of space, and we want to solve that. There are 2 important boundary conditions on the wave function that you must appreciate before we actually write down solutions to this differential equation. And those boundary conditions are listed because the barrier is infinitely high, right? That means that the wave function cannot exist for any value of x greater than L by 2 or for any value of x less than minus L by 2. So the boundary conditions for the wave functions have to be that the wave functions vanish at x equals plus L by 2 and x equals minus L by 2. And so those are 2 important conditions that have to be met for the wave function in this particular problem. What are the possible solutions for psi? Well, there's many ways to go about this. I find it easiest to say here is a possible solution. Then I leave it up to you to put that possible solution into Schrödinger's equation and actually show whether it can in fact solve the particular form of Schrödinger's equation for this infinite square well. So the 2 possible solutions that we're going to investigate are the sine and cosine solutions, right? And these 2 solutions naturally break into two groups based on the symmetry of the solutions. So we call the symmetric solution the cosine kx solutions. We call the anti-symmetric solutions the sine of kx solutions. And these symmetric and anti-symmetric solutions just refer to the symmetry of the wave function about x equals 0. And it provides a very convenient way to split the solutions up and discuss each class of symmetric and anti-symmetric solutions separately. You'll notice that these solutions also contain an adjustable constant out front, A and B. We're going to have to figure out what those values of A and B are in the process of solving Schrödinger's equation. So we'll go through that in this lecture also. The boundary conditions basically allow you to, the first question is, do these solutions actually work? And I worked through on this slide the arithmetic. It's pretty simple. You have to take the second derivative of each symmetric and anti-symmetric solution, and you end up with you turn the differential equation, right? You turn the differential equation into an algebraic equation, and then that algebraic equation allows you to solve for the energies of the symmetric solutions in terms of this wave vector k, which is embedded in the possible solution. Right? So there's a connection between the allowed energy E and the allowed k value k. And this is the case for the symmetric solutions. It turns out in this case, the anti-symmetric solutions have the exact same relationship between E and K. The issue is that not all K's are allowed for this infinite square well. The K's that are allowed must match these boundary conditions that we talked about a couple of slides ago. And so here we just apply those boundary conditions and show that the allowed values of K for the symmetric and anti-symmetric solutions, the allowed values of K have to be integer multiples of pi over 2, where n is an odd integer for the symmetric solutions and n is an even integer for the asymmetric solutions. So you can take these two conditions and combine them just into one, and so you can just basically say that the allowed values of K are equal to n pi divided by L, where L is the width of the well. So you have to tell me what L is. Is it 1 nanometer, 3 nanometers, 5 nanometers? Once you tell me that, then I can calculate the allowed values of K. And then once I know what K is, I can go back to the solutions of the Schrödinger equation, basically these two expressions for the symmetric and anti-symmetric energies. I can go back to those values, to those equations, and plug in the allowed values of K. And what I find is I find a range of quantized energy levels. Those energy levels are labeled by the subscript n, and that subscript n is just an integer, right? And those allowed energy levels contain a bunch of constants times this parameter n squared, right? So these constants depend on the mass of the particle confined in the well, the length of the well, and Planck's constant. So this is the prediction for the allowed energies of a particle in this infinite square well. The energy levels are not continuous, they're discrete, they're quantized, and they vary as this integer n squared. We also have to talk about the adjustable constants A and B that we're multiplying these symmetric and anti-symmetric wave functions. And the way those constants are determined is basically by a process called normalization, where we say we normalize the wave function. And so the issue then becomes, what does that mean? Because this is, again, a process that we're going to use over and over again throughout the semester. So the arithmetic here is pretty simple to understand, so I just wanted to go through it just to make sure you understand how to normalize a wave function, or to prove that a wave function has been normalized. If someone gives you a wave function, says it's normalized, how do you convince yourself that it is? So what do we mean by normalization? We basically mean that the integral of the square of the wave function integrated over all space is equal to unity. And so if you remember, psi squared is the probability density, and then you multiply the probability density by dx right here, That's the probability that you would find this particle at the position x within a region delta x, right? The normalization condition just states that if you integrate that wave function squared over all possible values of x, the probability that you're going to find that particle is unity, and that's why you set that normalization integral equal to 1. Now there's always a step, right? Because normally usually the normalization integral runs from minus infinity to plus infinity, but the problems we solve tend not to go from minus infinity to plus infinity. You're limited to a certain range in x. So these wave functions or the limits on the normalization integral have to be adjusted to match the problem that you're trying to solve. And this is something that you've got to do, right? If you understand the process, then you would immediately say, oh, the limits on this integral can't go from minus infinity to infinity because the well is only defined between minus L by 2 and plus L by 2. And so that allows you to rewrite the limits. And so now you can take one of those symmetric wave functions and you can plug it in here, and you can insist that that integral is equal to 1. So I do that, right? The rest of this slide, I just worked through the algebra. You have to check that out yourself. But at the end of the day, you find out that if you want that normalization integral equal to 1, this constant a has to be equal to the square root of 2 over L for this particular problem. Each problem is different, right? Each problem is different, and you have to be able to do this normalization integral in a routine fashion. So in a similar way, I'll let you work it out, but you can show that the odd solutions, the antisymmetric solutions to Schrödinger's equations have this constant b also equal to the square root of 2 over L. So for this problem, the constants a and b happen to be equal to one another. Okay, so that's important for you to understand. We can start to make tables of these solutions because there's multiple solutions to Schrödinger's equation, right? Each solution is often labeled by the quantum number n. So this is the constant, the integer value of n that basically quantizes the allowed k value of the particle in the well. This is the eigenfunction that then satisfies Schrödinger's equation for the particular quantum number n. These are the eigenvalues. These eigenvalues go as n squared. So I've tried to indicate that by by highlighting these red numbers that go as the square of the quantum number. And then lastly, right, you can define a constant E0, which is just this h squared over 8mEL squared, right? You can define that constant E0, and so then you can write the energy levels in a very, very convenient and transparent form. So there's no convention between different textbooks on how these eigenvalues and eigenfunctions are labeled. Usually you find that each eigenfunction and each eigenvalue is subscripted with the quantum number n, so that you can keep everything straight. So again, that's something that you have to sort of put into the problem yourself in order to categorize all these solutions. It sometimes helps to see the possible solutions plotted out, and so that's what we do in this slide. I just plot the first few of them. I plot psi 1, psi 2, and psi 3. Where the subscripts 1, 2, and 3 are these quantum numbers n. As you recall, the wave function itself in quantum mechanics is really not important. It's not measurable. It doesn't convey any information. It's just the square of the wave function that tells you what the probability is that you find a particle at a certain point in space. So once you know the wave functions, you then have to calculate the square of the wave functions, and it's useful to plot the square of the wave functions between minus L by 2 and L by 2, which is the extent of this infinite square well. And you can see that the shape of the probability distributions for finding this particle as a function of x are completely different depending on what quantum state the particle is in. And this is completely different from classical physics, right? There's no analog to this type of result based on classic physics. So I just remind you, for instance, that if you want to calculate what the probability is that you find a particle in the n equals 1 state at some position x, you have to go back to the fundamental definition of this probability density. The probability density is psi squared. You multiply that by the region in space, delta x, that you're trying to find the particle, and that tells you what the probability is that particle is located there. Now, if this wave function psi is properly normalized, so if the integral of psi star psi is set equal to 1, then this probability value is going to basically range between 0 and 1. And it just simply means that you'll have a unit probability of finding the particle in the box somewhere. But if you ask the question, what is the probability that you find it at a particular value of x, you then have to tell me what the range of dx is about that value of x. I multiply dx times the square of the wave function at that point x, and that then tells me the probability that if I did an experiment, I would actually find the particle at that particular point in space. So again, this interpretation is completely different from classical physics. Quantum physics, everything is about probabilities. The likelihood that you find a particle at a particular point in space becomes the critical issue. And for instance, it's cool to note that for some of these higher order solutions, there are regions in space where if you do experiments, you would never find the particle because the wave function goes through 0. That means that the square of the wave function is equal to 0. And that means that if you tried to measure a particle at this particular point in space, you would always get 0. It just never would be there. Lastly, the energy eigenvalues are plotted, right? They form a ladder of values. The energy eigenvalues are separated by n squared, right? And clearly, these graphs could be continued up to higher values of n. These pictures just go to n equals 3 for the wave functions and for the eigenvalues. You can put some numbers in, and I worked that out here just to show you that you can actually calculate the energy levels based on this parameter E0. So in this particular case, I pick a width of the infinite square well to be 5 nanometers. I evaluate this constant E0. Once I know what E0 is, then my energy levels are just n squared times E0. And these are the values of the energy levels for the first 4 allowed quantum states in this well. So you should be able, after this lecture, to take a width of a barrier, width of a well, and evaluate the allowed energy levels for a particle of mass m in that well using the results that we've derived in this lecture. And this is the essence of the quantum mechanics of the infinite square well. It's basically being able to plot the wave functions, the square of the wave functions, and then to construct a chart that shows the energy levels, the allowed energy levels for that particle in the well. So if you can do that, and you understand how to do that, then you've basically understood the important point of this lecture. I'm often asked, well, what situation in the real world approximates this infinite square well? Granted, the infinite square well in one dimension is sort of like a toy model. It provides a lot of insight. The results are reasonably easy to obtain. The results are analytical, so that's very nice. But is there a physical object where this infinite square well can be applied? And you can think of a few that might give you close approximations to an infinite square well. One approximation is if you have, let's say, a long chain linear molecule, right, and that molecule has some length L associated with it. If you trap an electron in that molecule, then basically the electron is confined to the region of space given by the length of the molecule, and perhaps the allowed energy levels that electron would experience when trapped in that molecule might be predicted by the infinite square well model. Another application is a very short channel, right? The channel length is L. We pretend that there's one electron trapped in this short channel. You can imagine that short channel is separated from electrodes on either end. You can imagine that these electrodes are biased negative so that there's no chance for the electron to ever escape from this channel width. And so maybe if you want to calculate the allowed energies of that electron in that channel, maybe that can be approximated by this infinite square well model, right? And you can then sort out allowed energies for the electron. So those are a few examples that you can imagine this infinite square well might apply to. So I think we have to stop right now. We're almost out of time. The next lecture we're going to complicate the discussion of electron states in a well. The well is still going to be a square well. The well is still going to be in one dimension, but we're going to relax the condition that the well has infinite height. And as soon as we do that, the solutions get a lot more complicated. But the basic idea that the energy levels are quantized, that still comes through, and we'll discuss that in greater length and more detail in the next lecture. So thank you. We'll see you for that lecture whenever you get a chance to view it.